I recently posted a video called Waveguide Demystified, but I didn't discuss anything about the waveguide's capability to handle power other than the narrow wall dimension matters for power handling. Theoretical formulas are available for waveguide power handling, but derating must be done because the formulas are theoretical and assume perfect waveguide conditions. The maximum power that can be transmitted through a waveguide will depend on the maximum electric field strength that can exist without breakdown. If the field strength can be specified, the maximum power handling can be calculated when the wavelength and the size of the waveguide is known. Experimental data on allowable field strengths at high frequencies indicates 30,000 volts per centimeter is applicable for air-filled guide at standard sea level conditions of temperature, pressure, and humidity. Equations given are theoretical maximum powers. Discontinuities, dirt, or dust will degrade power handling. Waveguide must also be properly terminated. The maximum power that a waveguide can safely carry is a fraction of the theoretical maximum calculated value, unless extraordinary precautions are taken. This is a type of formula you will often find in microwave textbooks for waveguide power handling, where P is the power in watts, A is the broad wall length in centimeters, and B is the narrow wall length in centimeters. Lambda is the free space wavelength of the signal transmitted through the waveguide. Lambda sub G is the waveguide wavelength. There is a relationship between the waveguide wavelength, the free space wavelength, and the wavelength at the cutoff frequency. But what is waveguide wavelength? This is a common formula you will see for waveguide wavelength, where lambda naught is the free space wavelength and lambda c is the cutoff wavelength. What the heck is that formula about, and where does it come from? Let's set that equation over to the side for a minute. Here's the basic relationship between the wavelengths. The inverse square of the free space wavelength lambda naught is equal to the sum of the inverse square of the waveguide wavelength plus the inverse square of the wavelength at cutoff, where lambda naught is the free space wavelength, lambda g is the waveguide wavelength, and lambda c is the waveguide cutoff wavelength. It has a form like the formula for resistors in parallel. Applying that concept, the free space wavelength will always be less than the waveguide wavelength and less than the cutoff wavelength. Now all we need to do is solve for lambda g. Here it is rearranged to solve for 1 over lambda g squared. Let's begin by multiplying both sides by lambda g squared. Multiply both sides by the least common factor, lambda naught squared times lambda c squared. Several terms cancel and we get this. Factor out lambda g squared, then divide both sides by lambda c squared minus lambda naught squared. Then take the square root of both sides and it gives us two solutions. So obviously the waveguide wavelength can be imaginary. Then simplify by removing the radical from the numerator. Then multiply the numerator and denominator by 1 over lambda c. Distribute 1 over lambda c into the radical. Then simplify the lambda powers. And here we have that textbook equation. Let's make some observations about this equation. If lambda naught is very much smaller than lambda cutoff, the denominator is approximately unity, and the waveguide wavelength equals the free space wavelength. As the free space wavelength approaches the cutoff wavelength, the waveguide wavelength increases and reaches infinity when the free space wavelength equals the cutoff wavelength. When the free space wavelength exceeds the cutoff wavelength, the guide wavelength is imaginary. This means there can be no propagation in the waveguide when the free space wavelength is greater than the cutoff wavelength. Let's calculate waveguide wavelength. using WR90 as an example at a frequency of 10 gigahertz. The broad wall of WR90 is 9/10 of an inch, or 2.286 centimeters. As you may remember from the Waveguide Demystified video, the cutoff wavelength, lambda sub c, is 2 times A. That gives us 4.572 centimeters. The free space wavelength is simply C over F, which comes out to about 3 centimeters. Plugging those values into our formula for waveguide wavelength gives us 3.976 centimeters. The useful ratio for the power handling equation is the free space wavelength over the waveguide wavelength, in this case 0.755. Now we can move on to power handling. Here's that power handling formula I showed at the first, where A is the broad wall length in centimeters, B is the narrow wall of the length in centimeters, lambda naught is the free space wavelength, and lambda g is the waveguide wavelength. Where did the 600,000 number come from? Well, it has the voltage breakdown in air at sea level baked into it. Here's the voltage breakdown in air, which is about 30,000 volts per centimeter at 1 atmosphere and 25 degrees C. In order for the voltage to be proportional to power, the voltage must be squared. Hence, the Ohm's law equation equals the voltage squared over the resistance. So 600,000 over 30,000 squared equals 6.66 times 10 to the minus fourth. Here's the other equation you will often see in textbooks for waveguide power handling. E max is the breakdown voltage. It's very close at 6.63 times 10 to the minus fourth. I don't know why it's often shown with E max on the left. Here it is rearranged to solve for power. Keeping with our example of WR90 waveguide, the broad wall A is 2.286 centimeters. The narrow wall B is 1.016 centimeters. Putting all that into our equation gives us 1.046 megawatts. Again, that's a theoretical maximum under perfect conditions and should never be used near that amount of power. When operating at higher altitudes than sea level, the atmospheric pressure decreases, so does the voltage breakdown. This is Paschen's curve. It represents the voltage breakdown versus pressure. The pressure at sea level is about 103 kilopascals. The breakdown voltage in air is around 30 kilovolts per centimeter. At 29,000 feet, the air pressure is about 31.5 kilopascals, so the breakdown voltage would only be about 13.1 kilovolts per centimeter. Doing the power calculation for 13.1 kilovolts per centimeter yields a theoretical power handling of only 199.5 kilowatts. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.